Hi, I'm Gal from Tel Aviv University, and this is joint work with my advisor, Gil Cohen, named Random Walks on Rotating Expanders. Many of you are probably familiar with random walks and with expander graphs, but you may wonder what are these rotating expanders I speak of, how do I define them, why do I define them? And what is going to be most interesting here are the tools which enable us to analyze these new objects. But first, let's set the stage for all those definitions. So what's an expander? There are several combinatorial definitions, such as vertex expansion and edge expansion. I will focus on the spectral definition of expansion, which goes as follows. I have an undirected n-vertex d-regular graph G, and I denote its adjacency matrix by A. G is undirected, so A is symmetric, so it has n real eigenvalues, also called the spectrum of A. And I can order them and name them lambda 1 to lambda n. We know that lambda 1 equals D. This is called the trivial eigenvalue of the graph. And lambda n is greater or equal than minus D. And we denote lambda of G as the max absolute value of all the non-trivial eigenvalues of the graph. And we have this magical number, lambda of G over D, which is a number between 0 and 1, which we call the expansion of the graph. The smaller it is, the better expander the graph is. And this number is closely related to the aforementioned vertex and edge expansions. And most notably, it is the rate of convergence of random walks on the graph. Now, the best expanders are called Ramanujan graphs, and they satisfy lambda roughly equals 2 square root of D. It is actually 2 square root of D minus 1, but I'm writing it this way to keep notations shorter here. Now, once we have an expander, many times we want to analyze random walks on it and also use it as a building block for constructing other graphs. And many times this is done by using what's called the power graph. So what's the power graph, denoted G to the T? It is a graph on the same set of vertices in which each edge represents a T-length walk in the original graph. So now the adjacency matrix becomes A to the power T. The degree becomes D to the T, which we now denote by capital D. And lambda becomes lambda to the T. This can be seen by looking at the spectral decomposition of the matrix A. And now a natural thing to ask is whether powering is good. Is it a good thing to do? Well, we started with an expansion lambda of G over D. This is a number between 0 and 1. We took it to the Tth power. T is at least 2. Then this is clearly smaller. It is better. But was this improvement worth its cost? Well, had we started with a Ramanujan graph with 2 square root of D, we take it to the Tth power, we end up with 2 to the T times square root of the new degree, meaning that the new graph is 2 to the T far from being Ramanujan. And this 2 to the T multiplicative factor is what we're going to try to handle in this work. Now, here's the first idea. What if I multiplied 2 different graphs? What do I mean here? Well, a power is just a special case for multiplication. So instead of multiplying the graph with itself, I multiply it with a different graph. For example, I start with G1, and I define G2 to be a permuted version of G1. I just rename the vertices, and I ask, would lambda of G1, G2 be smaller, be better than lambda of G1 squared? And the problem is that this question isn't quite well defined, as if I multiply 2 symmetric matrices, the product is not guaranteed to be symmetric. So this is not even an undirected graph, what I defined here. And in order to ask the proper question, I instead look at G1, G2, G1, which is guaranteed to be symmetric, and I square the middle graph for reasons that I won't get to in this video. In matrix form, this looks like this. I have a permutation matrix P, and I start with a square in the middle. I permute it, I rotate it once using this permutation matrix, and then I multiply by a from both sides again. Now recall, I'm not just interested in the square or the fourth power of the graph. I want to give an analog for the tth power of the graph, g to the t. And this leads me to the definition of the rotating expander. So I start with a graph G, and now I not only have one permutation matrix, I have a sequence of permutation matrices, and I define the adjacency matrix of the rotating expander the same way I just did, just I repeat the process more times. So I start with a square in the middle, I permute it, I rotate it once, I multiply by a again, I permute again, and so on and so forth, until I reach a degree of d to the 2t. And what I ask is, what is lambda of the rotating expander? Where I want to compare it to lambda of the power graph, which has this exponential dependency in t. And I keep in mind as a reference, what is the optimal value for this degree, which is the Ramanujan graph with this degree. And what we get in this work is a linear dependency in t for lambda of the rotating expander. Now, a few remarks about this result. First, have I just shown you the construction and let you analyze it? What you'd probably do is use some standard linear algebraic tools, or let's say the submultiplicativity of norms. And what you'll get when analyzing this construction using these tools is the exact same bound as for the power graph. And clearly linear is way better than exponential, which means that not only I need to show you this construction, I also need to introduce some non-trivial machinery in order to analyze it. And I will introduce this non-trivial machinery. Moreover, this isn't just an O of t notation here. This is the actual function with these constants, where E, Euler's number, just shows up naturally in the analysis. And we believe this formula to be, at least in some sense, tight. More about that towards the end of the talk. Formally stated, our result is as follows. For every Ramanujan graph G, there exists a sequence of permutations such that lambda of the rotating expander is bounded by the bound I've just mentioned, plus an error term that depends on d and t, the parameters, but also it depends on g, the girth of the graph. And it is actually dominated by a term of 2 to the minus g, meaning that if I start with a high girth Ramanujan graph, for example, the Lubotsky-Phillips-Sarnak Ramanujan graphs, which we know have girth logarithmic in the size of the graph, this term easily becomes negligible in comparison to the main bound. Now, once we reached this result, we actually looked back at the proof and asked ourselves, where exactly in here did we assume the graph was Ramanujan? This turned out to be quite a subtle discussion, which led us to the second and more surprising result, surprising to us, which is the following. For every deregular graph G, and I write here lambda expander, but I don't assume anything about lambda, there exists a sequence of permutations such that for large values of t, lambda of the rotating expander is bounded by the exact same bound. For smaller values of t, lambda is bounded by a constant times lambda times square root of d. Recall that in the power graph, we expected to see lambda to the t here. And not only we don't get lambda to the t, we don't even get lambda times 2 to the t, which is the trivial analysis for multiplying G with the Ramanujan graph, t times. Now we move to talk about the proof. And I first want to mention that our proof strategy closely follows a sequence of amazing works by Adam Marcus, Daniel Spillman, and Nikhil Srivastava. If you're familiar with their work, some of the ideas here may sound familiar to you. The proof consists of 4 components, and I'll briefly mention all of them, and I will elaborate more on the 2 highlighted in green. The first component is called quadrature. This is a term, roughly speaking, used for the translation between a discrete object and a continuous one. In our case, it will be between the choice of a random permutation matrix P and a Haar orthogonal matrix, a random Haar orthogonal matrix Q. More on what is the Haar measure over orthogonal matrices coming soon. The second part is the analysis of matrix multiplication, matrix products, using free probability theory. Free probability theory is a field which enables us to analyze random variables which constitute some specific relation between them, which is called freeness. And freeness is analogous to independence, but rather different from it. And we'll need, in order to analyze the matrices here, define the proper random variables that we want to analyze. The third part we call the cheat. We cheat by ignoring the graph and just analyzing some ideal object that we think of as an approximation of the graph. And only after doing all our calculations on the ideal object, we uncheat by looking back and bounding the error that might have occurred in this approximation. The fourth component is the interlacing families of polynomials, in which we are analyzing some expectation object, and the technique of interlacing polynomials enables us to deduce a result about a specific graph. So here's the first key idea for the usage of free probability. Assume you have 2 symmetric matrices, A and B, and we know how their spectrum looks like. This is a histogram of an actual spectrum of a 600 vertex 10 regular graph. And assume A and B have both this spectrum. And what I ask you to do is find the spectrum of the product ABA. The problem is that this is an impossible task. If I just tell you the spectrum, if I just tell you the eigenvalues, I tell you nothing about the eigenvectors, so you cannot understand anything about the dependencies between A and B. So there's nothing that can be said except for maybe some trivial bounds on the spectrum. So in order to have some hope here, we must introduce some randomness into the process. And the way we do it is by a Haar orthogonal matrix Q, a Haar random matrix Q, and we conjugate B by Q. Now, if you're not familiar with the Haar measure over orthogonal matrices, it can be described exactly how this distribution looks like, but what is more important, or what is more interesting, is what this conjugation does to B. Q is an orthogonal matrix, it is unitary, so the spectrum of B doesn't change at all, but all of B's structure just goes away. meaning that after this multiplication, B can have any set of orthogonal eigenvectors, all with the same likelihood. It can be thought of as after the multiplication with a random Q, B has the same spectrum, but its eigenvectors are in sort of this general position. They haven't been decided yet. And now it turns out that our hope was justified, because after this conjugation, we are able to analyze the expected spectrum of the product of matrices using something that's called the multiplicative convolution, denoted, the free multiplicative convolution denoted by this sign. Now, the multiplicative convolution is an operation on distributions. So now what I need to think of is this spectrum of the matrix as a distribution. The distribution is of a random variable, which is just picking a uniformly random eigenvalue of the graph, of the matrix A. And what I want to see is that after I convolute these two distributions, I get a third distribution, which will represent the eigenvalues of the product of matrices. A little bit more formally, how this is done is by defining this distribution, as I mentioned, the uniform distribution over the spectrum of the matrix. And then I encode this entire distribution into a transform, which is called the N transform of the distribution. You may be familiar with other transforms on distributions, such as the Fourier transform or the moment generating function, which are very useful in other scenarios. In the free scenario, it turns out that the N transform is rather useful. And after this encoding of the distribution into the transform, we are able to calculate the N transform of the product of matrices using the N transform of the matrices I started with. Now, this leads us to the second key idea of the proof, which is the cheat. I have told you that I used the N transform for the analysis, but I did not tell you what it was. And the N transform is actually the inverse function, inverse under composition, of the moment transform. The moment transform of the distribution mu is defined by this formula. And the problem that we face is this. We start, recall, with a graph G. We may know lambda of G. We may even know the entire spectrum of the graph. Now, after knowing the spectrum, we can define the proper random variable and calculate this M transform, which would be, in the discrete finite case, it would be a sum and not an integral. And then, in order to have the N transform, we need to invert this function to get N. And this just seems analytically impossible. And the way we handle this problem is by, again, ignoring the graph and just use one specific distribution, which is called the Kesten-McKay distribution. What is the Kesten-McKay distribution? It is parameterized by a number d, our degree, and it has its formula here, and also the visual representation here for d equals 3 and 4 and 5. And what we know about this distribution is, first, this is the distribution of the spectrum of the infinite DRE tree. And also, by the work of McKay, we know how to relate the moments of this distribution to the moments of an actual finite deregular graph using combinatorial qualities of the graph. In particular, the girth of the graph, which shows up in the error term that I've shown in the formal statement of the results. Now, again, a little bit more formally, what we do is, recall that we wanted to calculate the multiplicative convolution of two distributions to get the third one, but this seemed analytically impossible. So what we do is we use their idealized versions, the ideal objects, which are the Keston-McKay distributions, and we convolute them to get the third distribution that we're interested in. Now, I've shown the formula for the Keston-McKay distribution. It did not look that simple, but it turns out that its N transform is rather simple. This is actually the N transform of the Keston-McKay distribution squared. And through our cheat, this is an approximation of the N transform of the original graph squared. And using the formula I showed before, this can be used for the N transform, for calculating the N transform of the rotating expander matrix. Now recall, again, the N transform encodes all the information about the random variable, which represents the spectrum in our case. And we're not interested in the entire spectrum, we just want lambda. Lambda, in this case, is the bound on the support of the spectrum. So from this N transform, we're able to analyze what lambda is. I'll conclude with a few takeaways and ideas. First, we have the rotating expander, which has dependency in T for its expansion, which is linear in comparison to the exponential dependency in T for the power graph. Second, even though we are interested eventually in lambda, throughout the analysis, we use the entire spectrum of the original graph. And we do this by using tools from free probability theory. Some ideas. Well, I mentioned that there exists a good sequence of permutations, a sequence achieving this bound. What I would like to have is an algorithm that, given a graph, efficiently finds a good sequence of permutations. Second part is a lower bound. So I mentioned that there's a sequence of permutations achieving this. Maybe there exists a sequence of permutations achieving something much better, maybe even a Ramanujan graph. We have reasons to believe that this is not the case, but no lower bound is currently known. And we want to analyze the typical behavior of the rotating expander. We want to say that not only there exists a sequence of permutations achieving this, we also want to say that most sequences of permutations will be good, and this is supported by experimental evidence. So this is it, and thank you very much for listening.